By the end of the next decade, the first human feet will likely touch down on the dusty red soil of Mars. This is NASA's timeline, and it is by no means unrealistic. While that first visit might be similar to a stop-by, in line with the moon landing, some scientists claim permanent human colonies could be set up on Mars as early as 2050. That means it could be you, alive today and watching this, who sets out to tame that new frontier. You'd need to get into a space program pretty sharply if you're not in one already, but it is possible that you'll one day look out of a little bay window and watch as our pale blue dot vanishes into distant space. As you turn your gaze to your new home, what conditions can you expect to find on Mars? What challenges face any would-be Martian colonizer? What deadly weather will you encounter? What will the red planet throw at you? For unlike our home planet, Mars is a dead world, and anyone hoping to set foot there will need to overcome its daunting challenges with technology that is at the very cutting edge. Join us in this exploration of the environment of Mars as we explain both the hostile conditions and exactly what is being developed to help future Martians tame those arid, rusted wastelands. Stick around till the end for a very special announcement you don't want to miss. To colonize Mars, you first have to get there. The trip itself would take about 3 months with the most optimal launch conditions. This doesn't seem too excessive. It's like a long voyage on a cruise ship. But you have to consider that you would spend at least 3 months outside the safety of Earth's magnetic field. Out here, you are exposed to the solar wind and cosmic radiation. Prolonged exposure to this kind of radiation can cause astronauts to develop cancer and even symptoms of Alzheimer's before they reach Mars. Fortunately, there are some thoughts about how to protect against this. The astronauts could be shielded using materials in the ship's construction that are rich in hydrogen. In fact, the cabin could be surrounded by a water tank in the walls, water being rich in hydrogen. Another option is to create a magnetic field around the spacecraft, but this requires generating a huge amount of energy from a reactor small enough to fit on the ship, something we don't yet have the technology to do safely. Once there, for an alien planet, Mars is not as foreign as you might think. Earth and Mars share a lot of similarities, one being the length of day. The solar day on Mars is only slightly longer than it is on Earth, 24 hours, 39 minutes, and 35 seconds. Its year is slightly longer than ours, 1.88 Earth years, or 1 year, 320 days, and 80.2 hours. But that's to be expected for a planet that's further from the Sun, and so has a larger orbit. Of all the planets in the solar system, the seasons of Mars are the most Earth-like due to the similar tilts of the two planets' rotational axes, 23.5 degrees on Earth and 25 degrees on Mars. So what does that imply? It means Mars has summers and winters just like Earth does. Temperatures in the different seasons can vary quite a lot, and different locations can widen the range even further. Temperatures can be as low as -43 degrees Celsius at the polar winter caps to as high as 35 degrees in the equatorial summer. It has polar caps just like we do. During each pole's winter, the pole lies in continuous darkness just like on Earth. However, unlike on Earth, the temperature gets so cold that the atmosphere there freezes into slabs of CO2 ice, which collects on the surface of the permanent polar caps. These caps themselves are not primarily made of CO2, but instead are mostly water ice. The ice at the poles waxes and wanes. In this short visualization, you can actually see the differences in the size of the polar cap from the cap's winter to the cap's summer. One striking feature of Mars are the strange spiral patterns in the ice. Both of the poles show signs of these beautiful spirals, which scientists believe are a result of the Coriolis effect. The CO2 at the poles does not remain there forever. As the CO2 ice sublimates, it has a knock-on effect on another aspect of the planet, its winds. Sublimation of dry ice can create enormous wind speeds, which causes one of the most unique and terrifying aspects of Martian weather, its dust storms. If you peered across the rusted Martian surface through photos, you would be forgiven for thinking that Mars is a place of stillness. Flat, dusty landscapes stretching out in all directions with nothing but scatterings of rock and the faint whistling of the wind to keep at bay the almost oppressive solitude. But stay a while on this red world, and you would soon see a towering wall of dust and sand brewing on the horizon. You might think to yourself that this dust storm is similar to those we see on Earth, and have no idea that this storm is about to grow so large. Its thick dust will swallow up not just a region, not just a continent, but the entire planet. This all-enveloping superstorm arises on Mars usually every 3 Martian years, or about 5.5 Earth years. Its choking dust will blot out light for weeks, even months, and represents a huge challenge to the continued functionality of any technology placed there. If humans ever want to settle down on the red planet, it will be a hurdle we have to overcome, which is a problem, as there is much about the origins of these storms that we still don't know. Mars didn't always have to deal with planet-sized dust storms. Although it is now a barren, arid planet, it once had a thick atmosphere that was warm enough to support the existence of running water. However, over the course of billions of years, Mars dried out, and its atmosphere bled away until its atmospheric volume was less than 1% of what we have here on Earth. Those dust storms didn't just start happening because Mars became dry, though. While we don't understand everything about such storms' origins, we assume that a key component is Mars's temperature. With less atmosphere, in spite of its high CO2 levels, Mars became far worse at retaining heat. When the surface starts to cool, there is no air to catch the escaping warmth. It is at the point where if you were to stand on the planet's equator during its warmest time of the day, your feet might feel 23 degrees Celsius, while at your head it would be 0. As mentioned earlier, this means between day and night, Mars has some intense temperature swings. Temperature differences can cause winds to form, which can bring different weather systems across the planet. However, Mars's arid weather is no longer driven by rain and water cycles, but by cycles of dust. Dust plays a surprisingly crucial role on Mars, and without it, those planet-spanning storms would likely never form. The atmosphere might be too thin to capture and transport heat, but the Martian dust, that's another story. It all begins with that Martian dust getting into the air. There are a few mechanisms that make this happen. One is dust devils, of which Mars experiences thousands every year, usually during the Martian spring and summer. Warm rays from the sun heat the ground, causing the air directly next to it to rise and cool air from the atmosphere to be drawn down to fill the vacuum. These contrasting winds create rising spirals of air that can end up hundreds of meters wide and 8.5 kilometers tall, though many are much smaller. Regardless of their size, as they meander their way across Mars's all-encompassing deserts, they suck up dust and hurl it into the atmosphere, creating a haze of slightly darkened skies in their wake. This process is thought to contribute to a miasma of background dust that constantly lingers in Mars's atmosphere. While this is the flashiest way by which dust gets into the atmosphere, it's not the most prevalent. Far more common is the simple influence of wind moving across Mars's dusty surface and a process known as saltation. Mars's dust is surprisingly difficult to get up into the air. Small particles have a lot of cohesion due to being slightly electrostatic, kind of like packing peanuts. So they stick together, meaning they need a certain amount of momentum to get them going. Oddly enough, larger particles are actually easier for the wind to get moving, as they experience less cohesion. So it's these larger sand grains that are lifted by gusts of wind and moved for short distances. But because they are ultimately too heavy for the wind to suspend, they crash down again. And the force of these tiny impacts imparts enough momentum to overcome cohesion and get the lighter dust airborne. However, once it gets up there, Mars's lower gravity means that it's easy for dust to remain in the atmosphere for a really long time, weeks or months. And this is enough to start driving the formation of storms. Because unlike the thin air around them, particles of dust are really good at collecting heat from the sun. As the sun warms dust in the atmosphere, they act like little radiators, slowly releasing the gathered heat into the air around them. Previously, the warmth would have passed through the ground below, but now the dust in the atmosphere makes the nearby air much warmer. Warm air rises, but on Mars, this happens on a much larger scale than the smaller dust devils. As the air mass rises, wind is drawn in from the sides, adding more fuel to the process. More wind means more saltation, more dust being thrown into the atmosphere, and more opportunity for the air to warm. Eventually, this runaway process escalates into a regional dust storm. The good news is that, on a local scale, a dust storm on Mars is not very dangerous by itself. Wind speeds top out at around 97 kilometers per hour, only half the speed of hurricane winds on Earth. Even this is misleading. Because of the thin atmosphere, even fast-moving wind wouldn't feel like much. Unlike in some science fiction stories, Martian dust storms aren't powerful enough to topple spacecraft or break satellite dishes. But that doesn't mean they're harmless. Consider the case of NASA's Opportunity rover. On June 28, 2007, 1,200 souls into its mission, Opportunity was preparing to descend into Victoria Crater when the largest dust storm it had ever seen rolled in. The storm decreased sunlight by 96%. That sounds extreme, but some scattered light still reached the rover, allowing it to generate 128 watts of power on the darkest day, compared to its usual 700 watts on a clear day. For a solar-powered rover, this was a crisis. Power levels below 150 watts meant the batteries would drain, so operations were drastically reduced. Mission controllers commanded Opportunity to communicate only once every 3 days to conserve energy. If the batteries ran flat, the rover's components could be damaged by the extreme cold. Temperatures at the equator swing from 20 degrees Celsius during the day to minus 75 degrees Celsius at night. Initially, they thought the storm would last a week, but by July 15th, it had peaked. True color images showed just how dark it got. Fortunately, the storm didn't trigger a low-power fault, though it came dangerously close. By August 21st, Sol 1271, The storm had cleared enough for opportunity to resume operations. A lucky break. Not all rovers were so fortunate. Later that same year, the Spirit rover faced severe challenges. Martian storms had increased, covering its solar panels with dust and blocking up to 99% of sunlight. Power generation dropped to just 128 watt-hours, below the 150 needed to keep its heaters running. Without heat, the rover's components would fail. Two small cleaning events briefly boosted power to 372 watt-hours, allowing Spirit to recharge and move again. But its luck was running out. By April 2009, Spirit was experiencing unexplained memory gaps. On Sol 1892, it became stuck in soft, dusty soil at a site named Troy. The ground beneath its wheels was covered in jarosite, an iron sulfate mineral with low cohesion, making traction nearly impossible. Despite efforts by JPL engineers to free it, Spirit remained trapped. By Sol 2155, NASA reclassified it as a stationary research platform. It continued taking atmospheric measurements and images, including its final panorama from Troy. But as winter approached, power levels dropped again. By Sol 296, they were back at the critical 150-watt threshold. Sometime around Sol 2209, Spirit suffered a low-power fault and fell silent forever. The lesson is clear. Dust storms are deadly for solar-powered rovers. The sticky electrostatic dust blocks sunlight, coating solar panels and reducing power generation. But the problem gets worse when storms grow larger. Mars's orbit isn't perfectly circular. During southern hemisphere spring and summer, the planet is closest to the sun and at its warmest. For reasons still not fully understood, regional dust storms during this time often merge into continent-sized superstorms. These happen like clockwork every year. Even more mysterious are the planet-sized storms, which occur every 3 Martian years, about 5.5 Earth years. Scientists don't yet know why this cycle exists. It's too short to be explained by Milankovitch cycles, which operate over thousands of years. One theory is that the dust cycle needs time to recharge, but the exact mechanism remains unclear. Most dust storms last only a few days, but these apex storms can rage for weeks, with devastating effects on human technology. Scientists measure sunlight availability using aerosol optical depth AOD. On Mars, the AOD is usually around 0.5. For rovers like Opportunity or landers like InSight, an AOD below 2 is needed to charge batteries. Wildfire smoke on Earth that turns day into night has an AOD of 7. Martian planet-sized storms reach AODs of 9 to 11, near total darkness. In 2018, such a storm killed Opportunity by starving it of power. Without heaters, the extreme temperature swings damaged something critical, and the rover never woke up. Even nuclear-powered rovers like Curiosity face problems. The thick dust clouds block communications, forcing scientists to wait out the storms. Satellites aren't safe either. The warming atmosphere expands, increasing drag on orbiting spacecraft. They must burn fuel to adjust their orbits or risk crashing. For human settlers, these storms pose serious challenges. Solar-powered colonies would need backup energy sources. Freezing temperatures and communication blackouts would require self-sufficiency. If something went wrong during a storm, no help could come. Fortunately, the storms eventually die out. By blocking so much sunlight, they cool the surface, cutting off the rising winds that sustain them. What does Martian wind sound like? In 2018, the InSight lander recorded it using its seismometer. The vibrations, converted to audio, sound like a low rumble, best heard with headphones or a subwoofer. InSight also captured footage of water ice clouds drifting overhead, revealing wind direction. Despite its barren appearance, Mars still has traces of water vapor in its atmosphere. But the soil, could it support agriculture? Experiments with simulated Martian soil show that plants like tomatoes, rye, and quinoa can grow, though yields are slightly lower than on Earth. Moon soil, by comparison, produces about half as much. However, Martian soil lacks organic matter, so fertilizer is essential. In The Martian, the protagonist uses processed human waste, a viable solution if pathogens are removed. Another issue is toxicity. Martian soil contains heavy metals and calcium perchlorate, a salt harmful if ingested. Plants would absorb these, posing risks to humans. But perchlorate isn't all bad. It can extract water from the air and release oxygen, both vital for survival. Washing the soil or using perchlorate-eating bacteria could mitigate the danger. Growing plants is crucial for future colonies, providing fresh food and psychological benefits. Antioxidant-rich crops like tomatoes and blueberries might even offer some radiation protection. The key to Martian agriculture lies in adapting to the planet's unique conditions, fertilizing the soil and managing its toxins. NASA and other agencies are developing technologies to overcome these challenges. But rather than explain them all, let's hear from our special guest, who will introduce one of the most promising solutions. The atmosphere on Mars is extremely thin, making flight there seem impossible for a long time. However, collaboration with NASA's Jet Propulsion Laboratory has provided exclusive access to Ingenuity, the first helicopter on Mars. Ingenuity used ultra-lightweight materials and 2 sets of carbon fiber blades to complete 72 groundbreaking flights over its 3-year mission. It traveled more than 17 kilometers and captured stunning aerial images, demonstrating how engineers adapt technology to Mars's harsh environment. Helicopters aren't the only innovation being developed for Martian exploration. Another exciting project involves walking robots created in collaboration with Boston Dynamics. If you've followed Mars missions, you'll notice that all rovers, Spirit, Opportunity, Curiosity, Perseverance, and even China's Zhurong, share a similar design: 6 wheels, a large body, and scientific instruments. Wheels are efficient for flat terrain, but they limit mobility. Spirit's mission ended after it became trapped in soft sand in 2009, unable to escape despite efforts. Opportunity also got stuck in 2005, though it managed to break free after a month. Wheeled rovers face another challenge: steep slopes. During its first year, Opportunity explored Endurance Crater, where exposed rock layers held clues about Mars's watery past. Scientists hesitated because the rover could only handle inclines up to 30 degrees, and there was no guarantee it could climb back out. They took the risk, and Opportunity succeeded. But the mission could have ended there if the terrain had been too difficult. Now consider a different approach: walking robots. Boston Dynamics' Big Dog was an early example, capable of traversing loose terrain and the slopes far better than wheeled rovers. But it was their later model, Spot, that caught NASA's attention. Originally designed for industrial and hazardous environments on Earth, Spot can carry up to 14 kilograms, navigate uneven terrain, climb stairs, and even recover from falls. With a top speed of 5.8 kilometers per hour, much faster than a rover's 0.2 kilometers per hour, Spot's real advantage is its AI. It uses cameras to build 3D maps of its surroundings, autonomously choosing the best path and adjusting to obstacles in real time. This autonomy is crucial for planetary exploration. The distance between Earth and Mars creates communication delays of several minutes, making real-time control impossible. Current rovers like Spirit and Opportunity rely on pre-programmed commands, but Spot takes independence further. In tests with NASA's Jet Propulsion Laboratory, Spot has explored simulated Martian caves without human input, navigating darkness, dust, and water, while mapping the environment and identifying points of interest. Caves are a high-priority target for future missions. They offer protection from radiation, preserve geological and possibly biological evidence, and could even serve as human habitats. However, caves are difficult to explore from orbit, and traditional rovers can't handle their uneven, confined spaces. Spot, combined with JPL's Nebula AI, could change that. The vision is to deploy multiple robots that work as a team, mapping caves, analyzing samples, and relaying data back to the surface. While there's no set launch date yet, this technology could revolutionize planetary exploration. Future Mars colonists will need self-sufficiency. Communication delays mean no real-time help from Earth. Emergencies will require immediate local solutions. Once on Mars, where should they settle? The North Pole is a candidate due to its water ice, but equatorial regions offer warmer temperatures and better solar energy. Underground water deposits and lava tubes, natural tunnels formed by ancient lava flows, could provide shelter and resources. Before humans arrive, autonomous missions will prepare the site. Habitat designs vary, from ice structures to fungal-inspired architecture. But the key challenge is transporting materials. Not everything can be shipped from Earth, so in situ resource utilization, using Martian soil and ice, will be essential. The groundwork for these colonies is already being laid, with robots like Spot paving the way for humanity's next giant leap. Most proposed habitat designs for Mars rely on using the planet's abundant regolith surface soil in combination with 3D printing technology. However, the autonomous robots needed for this construction don't yet exist. They would first need to be developed before such a concept becomes feasible. The process would involve excavating Martian soil, mixing it with water ice to create a concrete-like material, and then 3D printing the habitat layer by layer. Robotic assistance and artificial intelligence would be essential in preparing these habitats before human arrival, as astronauts in bulky suits would struggle with prolonged manual labor. Once printed, the habitats must be strong enough to support additional layers of regolith piled on top for radiation shielding. Without Earth's protective magnetic field, Martian settlers face constant exposure to harmful solar and cosmic radiation. Burying habitats under several feet of soil provides crucial protection. After construction, colonists would still have significant work to do, setting up power systems, equipment, and life support infrastructure. Initially, they would likely live in cramped, temporary shelters, such as their landing craft or inflatable modules, while permanent habitats are completed. Creating a breathable atmosphere inside these habitats could involve electrolysis to extract oxygen from water ice, with the byproduct hydrogen refined into rocket fuel. Alternatively, carbon dioxide from Mars's thin atmosphere could be processed, as demonstrated by the MOXIE experiment on the Perseverance rover. However, these methods require substantial energy. Solar panels are an option, but Mars receives only 40% of Earth's sunlight, and dust storms can block sunlight for weeks. A more reliable solution might involve compact nuclear reactors, though such technology is still in development. The best approach would likely combine solar, nuclear, and battery storage for redundancy. Water production is another critical challenge. Settlers would extract ice from polar caps or underground deposits, then purify it through evaporation, condensation, and filtration, similar to systems used on the International Space Station. With efficient recycling, a steady supply could be maintained. Combined with oxygen generation and food cultivation, as discussed earlier, these systems could make a Martian colony self-sufficient. However, life on Mars would be far from easy. Confined to small spaces, isolated from Earth, and subjected to repetitive diets and high-stress workloads, settlers would face severe psychological strain. Even in extreme environments on Earth, like Antarctic research stations or submarines, crew members undergo regular mental health evaluations, knowing they can return home if needed. On Mars, there would be no quick escape, requiring settlers with exceptional resilience. Physical health is another major concern. Mars's low gravity